my channel, and today I'm going to be talking about solids of revolution. Notice that this topic involves integrals, which makes it a little bit more technical than any other topic in the field of calculus. So let's begin. We have to think of solids of revolution in a more intuitive and geometric perspective rather than a strict algebraic approach. So let's begin. Take a coordinate plane. On this coordinate plane, we're going to have a semicircle. So this semicircle over here is located on the coordinate plane. Now, let's spin this semicircle around its x-axis. What would we get? Well, we would get precisely a sphere. This is one example of a solid of revolution. Here's another. Imagine that we have a line. And we take this line in the first quadrant. And we also say that we're observing this line from the origin to, let's say, a point over here. Now let's spin this part of the line in quadrant 1 around its x-axis. What would we get? Well, we would get a cone. So now it may look a little bit easier to grasp what solids of revolution are. But the main part comes when we're going to start using the integral. We're going to use the integral to derive the volume of the resulting object that we're going to have. For example, a sphere over here, a cone over here. Okay. Let's take the semicircle example. Now, let's take a little bit of a rectangle in this semicircle. Now, if we take this little rectangle over here and we spin that around its x-axis, what will we get? Well, we would get a little bit of a disk over here. And this is why we're going to call the method which we're going to do today the method of disks. Notice that today we're only going to be covering solids of revolution from the x-axis. You could also revolve them around the y-axis, but we're just going to do the x-axis today. Continuing, we would just have the cylindrical object over here. Now let's just say this depth or width is called dx. So we're going to call this dl. We're going to say dl, or this little bit of rectangle, we're going to call the volume, is going to be about dx multiplied by the face of this vertical disc or vertical cylinder. Okay, so we know that cylinders have a circular essential shape on top. So we're going to have the area to be pi r squared. And we're going to multiply this with dx to get dl. But notice that since we're dealing with the coordinate plane, we're going to call heights y. And we have a specific reason to do this, which we will look at later. So we're going to call this pi y squared. Notice that dx is the width, then pi y squared is essentially this circle, the area. So we're going to multiply that to get the volume of this weird vertical disc. Okay, so this is going to be just one of the rectangles in the semicircle over here. Now if we take the integral of, let's just say, L, we're going to get the integral, well, dl is just going to be L. We're going to have pi y squared dx, and we're going to have the limits, a and b. And notice we've just derived the formula for solids of revolution. So we can use this formula to calculate the volume of any solid of revolution. So this is one of the key formulas that we're going to be using. Okay. Now, let's actually try to find the volume of a sphere. The volume of a sphere is just going to be pi r cubed. So this is going to be the volume of a sphere, and we're going to derive this from this semicircle over here. Okay, now let's just rearrange this semicircle so that it's on the origin. So this is going to be the semicircle, which we're going to call it symmetrical. But really, it's not symmetrical, but we're going to call it symmetrical because that's what we're going to treat it mathematically. So this is a symmetrical over the y-axis semicircle over here. So that means we're going to have the radius over here. So this is r, and this is going to be minus r. Now, let's just take the integral a to b. So we're not going to define the limits yet. And we're going to have inside pi y squared dx. Notice that we have a y variable and we're integrating with respect to x. Then what does this mean? Well, we're going to write y as the semicircle. So what we're going to do is that we know that a semicircle's equation is r squared minus x squared. Because we know that we're going to have x squared plus y squared is going to equal to, we're going to have r squared. So this is the formula for a circle. We can easily derive the semicircle formula. And if we're going to square this, we're just going to get r squared minus x squared for y squared. Simple. Now we're going to take this r squared minus x squared and plug it in to the integral. Okay, so we're going to plug it into the integral, and we're going to have r squared minus x squared dx. Okay. Now that we've got that, we just have to find the limits now. So what are the limits? Well, obviously the limits are essentially what the endpoints of the semicircle are. And they're r and minus r. So we can just replace this with minus r and replace this with r. Now we can actually start the integrating process. So we're going to get pi times r squared x minus x cubed over 3. Evaluated from minus r and r. So I'll just walk through how we got from this to this. So pi, we're just going to leave it outside, and we're going to have r squared. R squared, since it's not in terms of x right now, we're going to just add an x. For example, if we take a constant, let's just say the integral of 5, we're going to get 5x. Because 5 is just a number, we're going to add the x. Kind of like that, we're just going to add the x over here. The next part is x squared, or minus x squared. So that's just going to be x 2 plus 1 over 2 plus 1, which is going to be minus x cubed over 3. And we get that from x to the n plus 1 over n plus 1, the formula. So after we get that, we can just evaluate the integral from minus r to r. So first we're going to have r in this. So let's plug in r for the x's. So we're going to have pi times r cubed minus r cubed over 3. So this is what we're going to have for r. Okay, so right now it looks like we can't simplify it. But let's just multiply r cubed by 3 and divide it by 3. That makes sense because we're just going to have 3r cubed divided by 3. The 3's cancel out, so we'll just have r cubed. Which means that this is just precisely just going to be r cubed. So we don't have any relevant difference over here. So we can just have 3r cubed minus r cubed is just going to be 2r cubed over 3 times pi. Okay, now that we've got this, we have to evaluate it for minus r. Well, minus r, we're just going to have minus r cubed, and then minus r cubed, and then plus r cubed over 3. So we're going to have, So if we separate this, we're going to have minus r cubed plus r cubed over 3, since essentially the minuses cancel out because we're going to have a minus r cubed, minus minus cancel, so we're going to have a plus. Now we can do the same process, multiply 3 and divide by 3, and we're just going to get minus 2r cubed over 3. And we have to multiply it by pi, so therefore we're going to get minus 2r cubed over 3 times pi. Okay, now you may think, oh wait, these are just going to cancel. But there's one important step that you have to realize. Remember that we have to subtract this, so which means that we're going to have 2r cubed over 3 times pi minus 2r cubed over 3 times pi, which is just going to become plus, because the minuses and minuses become a plus, and therefore when you add them you get 4. This is going to be a plus, so we're going to have 4r cubed over 3 times pi, or 4/3 pi r cubed. And this is how we derive the volume of a sphere. Okay, let's review. So first, we derived the solids of revolution formula from the semicircle, and that can work for any solids of revolution. I'll write it over here. It's the integral of a to b of pi y squared dx. And remember, we're using the method of disks. So what we did next is that we found that the semicircle formula is just going to be the square root of r squared minus x squared. And when we square it, we just get r squared minus x squared. So we get that. And notice that we rearranged or repositioned the semicircle differently so that it's symmetrical on the y-axis, and which means the radius is going to be the endpoint. So the end of the radius is the endpoint, and the opposite end of the radius is just going to be the other endpoint. So if we take the radius over here, and we take the diameter, so one endpoint of the diameter is going to be the endpoint, and another endpoint of the diameter is going to be the endpoint. So which means that this is just going to be 2 radiuses, because this is one radius, this is another radius, and this is going to be in the negative x-axis, minus r, this is going to be in the positive, so we have r over here. So that's how we derive this. Notice that when we're taking the solids of revolution, we don't just have a sphere of infinite expanse, we have a sphere on these 2 endpoints, minus r and r. So we set that as our limits, and notice that we already plugged in. We did some integration, and we plugged in the values, and we got our formula, 4/3 pi r cubed. So that's how we get the solids of revolution formula for a sphere from a semicircle. Now let's do another example. This example was from the book, Mathematical Methods for Physics and Engineering. Okay. So this example involves a line. So we can erase this part also. So we're going to have a line, and this line is going to be y equals 2x. So that's going to be the function for the line, which means that this is how the line is going to be structured. Now, as we already mentioned, we're going to get a cone from revolving this, but we essentially have to cover the limits. Remember that without the limits, the whole volume will fail. So the limits are going to be x equals 0 and x equals h. H we can just essentially put over here, so x equals 0 and x equals h. So which means that we're only dealing with the first quadrant. So h essentially means that it can be anywhere. So we can pick an h, but it always starts from the origin. So this means that we're dealing with the first quadrant most of the time. Okay. Because this line doesn't go anywhere in the second quadrant. It only goes to the third quadrant and the first quadrant, which precisely means that we're only dealing with the first quadrant because x equals 0, and we're not probably going the other way. So we're going to consider that x is h is in the first quadrant, and let's start the process. So we're going to have the integral of, as we mentioned, h and then 0. So we're saying that h is greater than 0, which means that it's on the positive x-axis. And we're going to have pi times y squared. Y squared is just going to become 2x squared, which is just 4x squared, dx. And if we integrate this, we're just going to get pi times, if we take x squared, this is going to become x cubed over 3. So we're going to have 4/3 x cubed. And we're going to evaluate this from 0 to h. So if we bring this over here, we're going to have pi times 4/3. So we're going to have pi times 4/3, and then we're going to plug in h for x cubed. So we're just going to have h cubed. So 4/3 pi h cubed. So it precisely looks like the volume of the sphere. Okay. Now that we've got this, let's look at the last problem which we're going to be covering. The last problem which we're going to be covering is from the book Calculus by Morris Klein. So it states, if the portion of the line y equals x over 3 is lying in the first quadrant and is rotated around the x-axis, a cone is generated. Find the volume of the cone extending from x to equals 0 to x equals 5. Okay. Now this may seem a little bit wordy when considering the mathematical format it's in, but it's actually very simple. So as they already mentioned, we're going to have a cone because it's from a line. So we're going to have a cone, and we're going to have the line y equals x over 3. Okay, so x over 3, well, we're just going to have, so when x is 1, x is 1/3. So when x is going to be 3, y is 1. So x is going to be 3, y is 1. So precisely like this. So this is going to be the line y equals x over 3. Now we could just put the line over here. And the problem states that we're dealing with the first quadrant, which is over here. Which means that we're not going to deal with any negatives. Plus, Morris Klein mentions that we're going to have from x equals 0 to x equals 5. So from the origin to x equals 5, which is 1, 2, 3, 4, 5, to this point. So we have to rotate it from there. Now we just have to plug it into our formula, do some integration, and then we're going to get the volume. So we're going to have 0 and then 5 for our limits, because that's where we place them. So technically the endpoints. Y squared is just going to be x over 3 squared, which is going to be x squared over 9. So we're going to have particularly pi times x squared over 9. Okay, now that we've got this, we just have to do some integration. So if we can do it over here, we're going to have the integral of pi times x squared over 9 dx is going to be equal to, remember we have to write the limit, so 0 and then 5. is going to be equal to pi times, so x squared over 9 is just going to become x cubed over 27. Then evaluated from 0 to 5. Obviously, we're just going to have 5 cubed. 5 times 5 is 25. 25 times 5 is going to be 125. And therefore, we're just going to get 125 over 127. Well, not 127, just 27 pi. So this is going to be our answer. Now, you may be wondering, how did we get x squared over 9 to all the way to x cubed over 27? Because you may be used to seeing this, x to the n plus 1 and n plus 1, as I just mentioned earlier. Now, we already have a denominator over here, but if we think a little bit mathematically, and at this point algebraically, we're just going to have x squared times 1/9. And if we just evaluate this, thinking this is the coefficient, which it is, we're going to have x cubed over 3 times 1 over 9, which will just result in x cubed over 27. And we plugged in the 5, and therefore we get 125 over 27 pi as our volume. So that's how we essentially use the method of disks to our advantage for solids of revolution. Now that we've done all the problems, we can make this video to an end, but let's summarize. So in today's video, we covered what solids of revolution are. Solids of revolution are essentially when you take a 2D object or two-dimensional object and rotate it around its x-axis or y-axis. In this video specifically, we covered the x-axis, and it's called the method of disks. Notice that we derive the formula for any solid of revolution, which is the integral from a to b of pi y squared dx. And remember, we have to write y squared as in terms of x, and this is going to be our complete formula. Then we did 3 examples. The first one we actually did for a sphere, and that's how we derive the formula for this sphere, for the volume of this sphere, which is 4/3 pi r cubed. Next, we covered from the book Mathematical Methods for Physics and Engineering how to essentially compute the essential solids of revolution from the line y equals 2x. And then after that, we covered another problem from the book Calculus from Morris Klein, and the problem was with the line y equals x over 3, with limits from x equals 0 to x equals 5. Then we covered that, and we got 125 over 27 pi as our answer. Okay, now that we've talked about that, we can make this video to an end. If you like this video, if you like this channel, please subscribe to learn more. Thank you.